We are in Chapter 2. This is Section 2.1. We'll be talking about interval notation, relations, and functions. So first, for interval notation, if we use the parentheses, we're not including those endpoints. And if we use brackets, then we are including those endpoints. So parentheses, not. Brackets, we are. Here are a couple of examples. So if x is greater than or equal to 7, we would write the interval from 7 to infinity. The bracket would include the 7. We don't include the infinity because it's a symbol. Negative 4 is less than or equal to x is less than 2. That's negative 4 to 2. We include the negative 4 but not the 2. X is less than 4. Again, we don't include the symbol of negative infinity. We don't include the 4. Negative 1 is less than x is less than or equal to 5. We don't include the negative 1. We do include the 5. So we use that throughout. Okay, next we have a relation, and if we're talking about the domain in this relation, it's the input values, the start values. So that's 2 and 4 and 3, and there's another 2 and we don't repeat that. The range are the output values, sometimes called the y values. So that's 3, which is repeated, and then negative 1. It is a relation, but in this case it is not a function, because for a function to exist, we need to have every input value has to have a unique output, and 2 maps to 3 and 2 maps to negative 1, so it's not a function. Okay, on to 1D. This is a relation. It's also not a function. Typically we think of x as the input, y as the output, and here we can get that input of 3 with 2 different outputs, 1 and negative 1. So again, because we have an input value that maps to 2 different outputs, that means that it is not a function. You find one counterexample, it's not a function. Let's extend that idea though, and instead of x equals 2y squared plus 1, let's try y equals 2x squared plus 1. This is a relation, and this is a function. This is a function. We set up a little table and we plug in some x values, find some output values. The output values are unique to each input value. They are unique to each input value, so it is a function. Now if we look at two ordered pairs, negative 2, 9 and 2, 9, we see that we get the same output for 2 different inputs, but that's okay, right? That's okay. So notice the difference between 1D and 1D's extension. One is not a function, and then the other is a function. Okay, let's take a look at a couple other problems where we're trying to find the domain. So 2A. The function here is a fraction, x plus 4 over x squared minus 2x minus 3. It's factorable, so we factor that denominator. And if we're looking for the domain, we don't want zeros in the denominator, so we write that in interval notation. Negative infinity to negative 1, union negative 1 to 3, union 3 to infinity. And of course, we should also be able to use set builder notation, again excluding the negative 1 and the 3. Here's another one, 2c, where h of x is the square root of 3 minus 2x. What's inside that root has to be non-negative in order for us to get a real output. So x is less than or equal to 3 halves. So if we write that in interval notation, it's negative infinity to 3 halves. Again, the 3 halves, the 3 halves is included, and the negative infinity is a symbol. It's not. Again, set builder notation should also be used. Next is a word problem. We've got a rectangular garden with a perimeter of 100 feet. We draw ourselves a little diagram. Here's the perimeter formula. We want to find an area function, so let's isolate the L. And we can say L is equal to P over 2 minus W. We know the perimeter is 100, so we can further write L as 50 minus W. Area is just length times width. We replace the length with what we know it's equal to. We multiply that out using the distributive property, and there's our area formula. And the domain, well, we don't want an area that is either 0 or negative. So our domain has to be a W value from 0 to 50, excluding 0, excluding 50, because we don't want a value of 0. And we should also be able to use set builder notation. There we go. Okay, next we're going to be finding the domain for some combinations of functions, subtraction, addition, multiplication, and division. And when we do that, we want to find the intersection of the domains of the two functions. There's an added restriction if we are trying to find the quotient. So here's an example with two different functions, f of x and g of x. And if we do 4b, we're going to find the difference of those two functions. And you can just write them out. Subtract g from f, use the distributive property with that minus sign, simplify, and we get 5x minus 10. So that's f minus g of x simplified. 4d is a quotient, so if we write the quotient and simplify, we find that we can factor both numerator and denominator, and that allows us to simplify this because there's a common factor of x minus 2 up above and down below, so we get a nice simple expression, negative 2/3. All right, now let's find the domain for each of these. So the domain is going to be the intersection of the domain of f and the domain of g. There's an added restriction for the quotient. Okay, so they're both all reals, so that means that if we take the intersection of those two, it's also all reals, at least for 4b. Relatively simple. 4d is a little bit more complicated because we have to add the restriction that the denominator can't equal 0. So g of x cannot be equal to 0, and that means that x can't be 2. So the domain is the intersection of the two domains of f and g, and then the added restriction that the denominator, the g of x, can't be 0. So there it is in interval notation. Of course, we should also be able to write it in set builder notation. All right, if we take a look at 4e, that's the sum of two functions, and here we're going to find it at a specific value of 1. So we find the function at 1, f at 1, and g at 1, and then we just add them together. Do a little simplifying. So we get negative 2 for f of 1, and we get 3. We add them together, we get 1 total. 4g is similar, but it's going to be a product, and it's going to be at negative 1. So we find f at negative 1, we find g at negative 1, and we simplify those. And f at negative 1 is going to be negative 6, and g at negative 1 is 9. We multiply, and we get negative 54. So we should be able to do those types of problems. Moving on, a couple quotient functions. And for 5c, we're going to find the product of these two functions and then talk about their domain. So we're just going to multiply one by the other, clean it up a little bit. So we get x over x minus 2 times x plus 4. And we want to find the intersection of the two domains. So x can't be 2, x can't be negative 4. That's the intersection of the domain of f and the domain of g. And so that's the domain of my new function, f of x times g of x. And we can write it in interval notation. And we should also be able to write it in set builder notation. So we exclude the negative 4, we exclude the 2. Of course, we also exclude the infinities because they're symbols, they're not numbers. 5d, we're going to take the quotient of the two functions, so one fraction over another, and then we simplify that idea. And we've got x plus 4 over x times x minus 2. We're again looking for the domain, so it's going to be the intersection of the domain of f and the domain of g. The added restriction, though, is that g of x can't be 0, and that means x can't be 0. So we take all those restrictions together. X can't be 2, can't be negative 4, can't be 0, and we write it in interval notation using the union symbol. And there we go. Put them all together. And of course also in set builder notation. So just as a reminder, when you're trying to find the domain of one of these combination functions where you're adding, subtracting, multiplying, or dividing, you've got to find the intersection of the two functions. If it's a quotient, you have the added restriction.